Hello everyone, good morning, good afternoon or good evening, wherever you may be, and welcome to this Amazon Web Services webinar AWS 201, Measuring Your Application Performance and Health. My name is Markku Lepistö. I'm a technology evangelist at AWS, working out of Singapore. Now this webinar is a 201 level webinar, which assumes that you have a basic understanding of AWS services and cloud computing concepts in general. Now first, let's take a look at some housekeeping items. I will run through the presentation slides, and this will last roughly, give or take, 40 minutes or so. While I'm presenting, please utilize the online chat window in your webinar system to post questions. And our AWS folks will be answering as many of those questions as possible online as I'm presenting. And after my presentation, we can still continue for 10-15 minutes or so to have more Q&A, so we can continue posting questions, and after the webinar we will still continue answering as many as we can. And then a reminder, please do fill in the survey. AWS loves customer feedback, and that allows us to iterate and improve our services. Now, without any further ado, let's simply get going. Let's start with the question why. Why would you monitor something? Well, basically, if you don't monitor without instrumentation, you are flying blind. But with instrumentation, you get benefits such as actionable insights. So these actionable insights can help you drive your business. You can have insights on the historical performance of your system, the current state, health performance, and maybe also the predicted or future state of your system. Now your system here could be your application, or your product or your service. And then by instrumenting your system, you can make data-driven decisions, and you can have a feedback loop. When you change something in a feedback loop, you can actually monitor and measure what is the expected output. So if you do a change, does it change your system for better or for worse? And instrumentation also gives you operational efficiency. Items such as availability of your system, performance, cost optimization, and maybe, if you're developing software, your release cycles, speed and quality, and many, many others. If you don't monitor and measure, you don't know what you are doing, and you don't know if your changes are affecting for the better or for the worse. So those are some of the highlights, high-level view, why you should be monitoring. Next, let's take a look at what exactly you should be monitoring. Well, if you look at the business ones on the left, they are KPIs. A KPI is a key performance indicator, in other words, a metric. So they're business KPIs, such as your business transactions. How many transactions did you serve to your customers based on your customer requests? Then, what is the quality of service of your customers? This is very important. This is a high-level metric showing you what is the actual service level that you are providing for your customers. And then, going forward from that, is customer quality of experience. Do they have a good experience, bad experience? Ultimately, your business people will want to monitor your revenue, your incoming transactions and business, and also the associated cost, and many other metrics. On the operational side, you are definitely interested in transactions. These are requests from your customer that you serve as responses from your system. So you will want to know the success rate, the error rate of your system, and the latency, how fast or how slow is your overall service. Also the throughput, how many customers, what is the volume, what is the speed at which you are able to actually scale out your service. And then, what is the implied load on your system from the customer traffic? On system level, on services level, then on node level, on smaller granularity, and on component level, where the component could be, for example, a piece of code. So you want to know the load on your system. You will want to know the health of your system and the general availability of your system, and many, many other metrics on the operational side as well. Now, what are we actually measuring? Basically, it all boils down to this. We are measuring system inputs, state changes in your system, and then outputs back from your system. So we are talking about delta. So what actually causes these system changes? The first one is typically the customer input. So as customers make a request to your service, that is traffic and that is an input into your system. Code changes also cause changes in your system state. If you add features, if you modify features, your system will likely behave in a different manner. So that is a change. Manual operations cause system changes. So there's a kind of a joke there that you may go from ops, so operations, to ops. I didn't mean to do that. Quite often, unfortunately, humans make mistakes. And even if you don't make a mistake, when you make a manual operation, you are actually changing something. So that implies a system change. When we talk about cloud solutions and cloud services and products, automation is key. So definitely you will have some automated operations that change your system based on some inputs automatically without human intervention. Actually, sophisticated cloud applications are, in effect, complex adaptive systems. There's a whole range of books and theories on this particular topic. It's not simply related to cloud computing, but a cloud solution may actually be a complex adaptive system. Definitely, when you have operating system packages and patches that are changing in your system, that is a change. And your system behavior might change when you, for example, upgrade an operating system package. Maybe that module or service that you're using on the operating system side becomes slower or less reliable or faster and more reliable as a result of the change. Anyway, it's a change that will cause delta in your system. Dependent services cause changes in your system when they change. So basically, more and more, you are relying on services. You are focusing your development on your application logic, but you are outsourcing undifferentiated heavy lifting to services, such as Amazon Web Services for compute, storage, networking, and higher level services. You may use some other third-party services. If and when there are changes in these services, those changes will also maybe reflect on you because you are requesting something from these third parties. There may be domino effect or cascading effects when a service changes down the stream. And ultimately, everything is running on top of some infrastructure. Your clients use some infrastructure on their side. There's the whole internet with ISP connections, all kinds of switches, routers, firewalls, etc., network equipment, etc. And then your system is running on infrastructure as well. So any changes on the underlying infrastructure end-to-end will also cause system changes. So you will want to capture these system changes, understand the current state, and if necessary, act on these changes. So when should I measure something and where should I measure something? Basically, you should measure everywhere and you should measure all the time. Because now, with cloud computing and big data, now all of a sudden the cost of storing information is less than making the decision what data or what information to keep and what information to throw away. There's a nice quote here from Mr. George Dyson. You can see the quote on the screen here. That is really the fact now. And as a result, nowadays we recommend that by default you should monitor everything. Maybe later you can disregard and stop monitoring some parts of your system, but at least start by monitoring absolutely everything. Otherwise you're flying again with your eyes closed. Ultimately, when you're collecting something, next you need to analyze what you have collected. Then you need to display what you have. You need to display the information in a meaningful manner. And then ultimately you need to actually act on the information. The first three actually are meaningless unless somebody acts on the information. So let's take a look how we could implement this end-to-end process-wise. Let's start with the information collection. So the question is, when should I measure something and collect the information, and where should I measure and collect? The first axis here is time. So when it comes to time, you have your application, your product or service. It has a life cycle from the beginning to the end of the lifetime of your application. So that axis is time. The second axis is the end-to-end view from your customers and their client applications, their client devices, all the way back to your product, your servers, and the services that you're relying on. So there's the end-to-end view physically. And the last axis is the top-to-bottom view. Basically, it's the technology stack that you are using to implement your application. So you should be measuring at least all three of these axes. Now let's take a look at them one by one. Let's start with the time. So the question related to time is, when should I measure something? Well, you should measure and monitor throughout the application's lifecycle. Here we have a nice example view showing how the application development, testing, deployment, and operating procedures have evolved from agile to continuous integration through continuous delivery to now the best practice, which is called DevOps. That's a large topic on its own, but the main idea is that you will have end-to-end automation, you will have agility, you will have lean methodologies, etc. throughout your entire life cycle, from planning your code changes and features to actually coding them, building, testing, releasing, deploying, and then operating them. Automation is one key aspect of all of this, and also related processes. So let's take a look when you should be measuring at some of these main stages here. So let's start with the coding phase here. So coding phase is when your developers are implementing either bug fixes or new features. So this is a time to measure something. What should you be measuring here? Well, for example, you should be measuring the code commits, how many commits your developers are doing, how many lines of code they have been changing, which software modules have had changes, how many bugs do they claim that they have resolved, it hasn't been tested yet, and how many features do they claim that they have implemented as new code. And as you move on to the build phase, then your automated build systems will be definitely building your latest code releases. And then you can be measuring how many builds were successful, how many builds failed because maybe some bad dependencies, bad commits. How long did it take your systems to actually make the build, to compile the system, versus how many hardware or virtual hardware resources you threw at the compilation. It's not enough to measure the build duration if all of a sudden you double or tenfold the number of virtual machines doing the build, for example. So one nice indicator would be the build duration as a function of hardware resources used. And ultimately, your build system is producing, for example, images, which may be Amazon AMIs for EC2. So what is the number of images that you have built over time? As we move to testing, there are different stages of testing that we recommend. For example, integration testing, which is the first time that the different components after unit testing come together and try to interact, maybe also with some third-party services you're relying on. So how successful or unsuccessful is the integration testing? That's a metric. Performance testing is very important. Some people call it load testing or capacity testing. You will want to verify that your product or service can actually handle the load. And definitely you should be testing at least the load you're expecting, and the recommendation is to test far higher load than you are expecting in production, because you might have all of a sudden success peaks or burst traffic coming into your system. So what could you be measuring here? Well, for example, you could be measuring first of all that your system can achieve the throughput required, like transactions per second. And as I mentioned earlier in the build system, maybe you want to measure the throughput as a function of hardware used. So again, it's easier to reach a high throughput from your system if you throw a lot of hardware or virtual machine instances on the problem. However, that's not really cost efficient. That's not optimized. You may want to downsize, for example, your EC2 instances, optimize the EC2 instance size, and then the number of instances required to actually serve the target traffic, for example, 1,000 or 10,000 transactions per second. So you need to do iterative testing, measurement, and then optimizations. And you cannot optimize unless you measure the actual results. So as you do a performance test, see that you are first of all able to reach the target, and then how much hardware did it take. And then your developers can iteratively optimize the system and then maybe use less hardware resources, which is more cost efficient. But there's always a balance. How much fine-tuning actually costs more money and resources in the form of tuning versus the benefits gained. Then you have stability testing. You will want to know that once you have code changes, that your system is still stable. Maybe there are also associated operating system and other third-party packages that have changed. So there's a lot of delta. You will want to test the stability of the release. For example, just some examples, you want to measure, are there memory leaks, maybe in your application or third-party components? What about your file system trending? Do you have actually cleanups and log rotation, or are some of your volumes filling up because you are not cleaning up some files? Over time, your system may then crash because it runs out of some resources. So overall, in your stability testing, you want to know, is my system having degradation of any of the KPIs over time? And then do projections. A good practice is to run the stability test at least several days, even a week, depending on your practices. Then we have security testing. That's not to be underestimated. One example of them is, for example, automated penetration testing. So as you have new operating system packages, third-party libraries, and your own code changes and configuration changes in your system, it is really a best practice to execute automated security tests to ensure that you don't have any new holes open, for example, in your system, or new vulnerabilities. Moving on, you have passed the testing phase. Now you want to deploy something. You can measure a lot of things, for example, number of releases over time. So release is something that has passed testing. Then you have deployments when you actually deploy them into production. Sometimes you may need to roll back or switch the traffic back to the previous version of your code base. And then you have all the operational KPIs, such as your system stability, availability, performance, security, etc. Now, that's not the end of it. Then you have an interesting feedback loop here. Once you're in operation, you will only then truly know how your system is behaving. Then you will have inputs back to your system, which are, for example, bugs reported, and then feature requests from your customers. So those are, again, inputs back into this loop. And interestingly, as we now start using DevOps best practices and methodologies, processes and tooling, and cloud computing, DevOps and cloud together actually increase the rate of change in a system. If we first look at the right-hand side of the picture, with the Waterfall development model, where you did a lot of upfront planning, slow development cycles, and you were typically using legacy IT, which means static servers, maybe physical servers that were pre-allocated, the rate of change was very slow. Your servers were long-lived. They were doing the same thing for a long time with few changes. And the IP addressing, for example, was pretty much static. It didn't change. Now if we look at the left-hand side, DevOps plus cloud, you have frequent releases, and your instances or servers are dynamic and ephemeral. So you will have methodologies like Agile, Lean, and DevOps in use, a lot of releases. And when you have a release, you will have a burst of new instances. So what many companies do, for example, is that instead of upgrading the instances that are running in place, they simply deploy new instances in EC2 and then run the new version of the code on the new instances. Then with, for example, elastic load balancing or Route 53, you can send a part of your customer traffic to the new release on the new instances. If everything looks fine, you can send more traffic and ultimately fail or switch all the traffic from your old version to the new instances running the new version. Then the rollback is simply a matter of switching the traffic back from the new to the old instances. So from monitoring point of view, this means that with DevOps and cloud, there's a lot of change. The rate of change is much higher with DevOps. And then the monitored instances, what the monitoring system is using as the data sources, are coming and going all the time. In large bursts of new instances all of a sudden, the roles of the instances may change. And the IP addressing of the clients, the agents if you will, where you collect the information, are dynamic by nature. And in the cloud, those IP addresses of your servers might even be recycled. As you release some EC2 instances and deploy more, some of them may get back some of the IP addresses you were using earlier. So this could be a problem for some of the legacy monitoring systems that don't understand this rapid rate of change and definitely don't understand that, for example, a client or monitored system IP address will all of a sudden behave differently and the system will have a different role for that IP address. So this is a challenge for monitoring systems. Now, moving on, we are still talking about when you should be measuring something and where should you be measuring and collecting this information. Let's now take a look at the other axis, end-to-end view, from client to server. So in this picture, I have tried to depict a really simple use case. You have your customers and clients on the left. You have transport systems that are transmitting your client request all the way back to your service, maybe running in AWS. You have your application there. You are using AWS services for your product. You may be using compute, storage, networking, auto-scaling, maybe CloudFront, maybe big data services, maybe RDS for databases, etc., etc. So your application or service actually consists of your code implemented in the purple boxes as well as outsourced services, some of them coming from AWS. And then the blue box on the bottom right are third-party services that you also need to implement your ultimate solution. So you might have, for example, social logins here, in-advance credit checks, some billing systems, etc., etc. Third-party systems. So how would we be measuring and where should we be measuring here? Let's start on the left. The clients. Well, definitely you can have test clients. So you have real customers who have their own clients. You can also deploy your own test clients as a customer, if you will, your own customer. On your test clients, you can insert agents, which can be collecting the customer perceived quality of service and quality of experience of your product. In some cases, you may be able to run some monitoring agents on the real customers' devices as well. The customers may opt in, for example, for this data collection to help you improve your service. Now, definitely you shouldn't be collecting any identifiable sensitive information, but some operational information, for example, showing your system latency or packet loss, for example, as an opt-in for your customers. Then, let's talk about the transport. How does your client request reach your system? Well, it has to pass through all these transport networks and devices. Typically, these are black boxes. You cannot really have any of your monitoring agents. You cannot get the information from within the system. So, typically what you do is that you measure end-to-end. So you have your clients, especially your test clients. You can run TCP dump. So basically, IP packet capture on your client devices, especially the ones that you have deployed yourself. On your servers, which are serving the requests and receiving the request, you can also run TCP dump, capture the traffic. Then using freely available tools, nice tools like Wireshark, you can analyze the network quality of service, the transport between your clients and your servers. Here, this is an actual graph showing with the transport analysis end-to-end a problem on the server side that the client was facing. And this problem, this is a real-life scenario, this problem was actually affecting the clients, but because the problem was on the transport layer, on the network layer, it was not visible on the application layer. So the application error messages, the application logs were useless. Only when analyzing the low levels of the stack were we able to see the problem. So here, for example, on the top, we have one graph which shows the server, and the particular graph or metric is the TCP0 window. Now TCP0 window means that the server, when this graph starts increasing, the server is not able to process the packets coming into the server. So your client requests come to the server in the form of packets, but zero window means that those packets are being buffered on the server and the actual application is not reading them from the operating system TCP/IP stack. So something was wrong in the application. The client was able to see this in the form of ultimately TCP resets. So here we have clients timing out on the TCP/IP level and resetting the connections. So basically those clients have very bad quality of service now. Moving on. Next, let's talk about monitoring AWS services. So your ultimate solution or product in purple is relying on many AWS services for work. How do you monitor AWS itself? Well, we have, for example, the AWS Service Health Dashboard, and then we have services like CloudTrail and CloudWatch. Now let's take a look at some of these in more detail. The first view into the overall health of AWS services is the Service Health Dashboard. You can see the URL there. It's simply status.aws.amazon.com. You can choose the regions you are interested in, and then you can see an online, up-to-the-minute, real-time, high-level view of the health of the AWS services. And there will also be, of course, notifications, information if needed. Next, we have AWS CloudTrail. With AWS CloudTrail, you can easily implement an audit trail. An audit trail means that in many cases, especially in the enterprise world, you need to know whether you have governance and compliance in place when it comes to change management. Who is able to change systems? Who is allowed to do changes in production, for example? Who has actually done changes? Why, when, and where in the system? So AWS CloudTrail is an enabler for this. Basically, as you are interacting with the cloud using many of the different interfaces like command line, the console, Elastic Beanstalk, etc., ultimately you and your people are making API calls. They are making API calls on the growing set of services that implement the AWS cloud, and CloudTrail can continuously record these API calls from your users to the system and then store them as log files. And ultimately, these log files need to be analyzed. So we have a large ecosystem of partner tools already available that enable you to do monitoring and analytics on this audit trail. You can see some of the examples here like Boundary, Sumo Logic, SecondWatch, etc., and Splunk, and many others. So that's an audit trail enabled by CloudTrail. Next, let's talk about monitoring the AWS resources themselves. And for that, we have Amazon CloudWatch. And this is what Amazon CloudWatch looks like if you use the console, the web console. So here we are in the CloudWatch console. And we have an example graph here, CPU utilization of one of the EC2 instances. Basically, with CloudWatch, you can measure and monitor a lot of AWS services. I will not read through the list, but you can see here that a very large number of the AWS services in our portfolio can be measured and monitored leveraging Amazon CloudWatch. And monitoring is not enough. With CloudWatch, you can also set alarms. Alarms which are notifications and alarms that can ultimately have associated actions then. Here we have a couple of use cases. So for EC2, you might be interested please tell me if my instance needs any attention, if it's running out of resources, if it's feeling a bit sick, unwell. For DynamoDB, for example, you may want CloudWatch to help you balance the cost and performance. For billing, that's quite typical use cases that you want to know when your bill is getting too high, basically exceeding a threshold. So what you can do very easily is that you can have CloudWatch send you alarms. So this is just a simple example of an email that a user has received based on a CloudWatch alarm, that a resource has exceeded a configurable threshold, and that has then generated this alarm. And the notification has been in the form of email in this case. Now we have a set of standard metrics, a large number of standard metrics coming out of the different services monitored by CloudWatch. But very interestingly, in this webinar we talk about application monitoring. You can also have custom metrics inserted into CloudWatch from your application. And this adds value for your application monitoring. Well, let's have a quick example here how we could be monitoring the memory of an instance using custom metrics in CloudWatch. So we start in the EC2 console. We will select one of the instances that we want to monitor. Ultimately, you will want to automate this, but I will show you here the manual way of doing it. We select an instance. We connect to the instance. This is Linux. So we will be SSHing into the instance. Here we are. Let's clear the screen. And then let's make a directory of AWS monitoring scripts. And what we have provided a set of CloudWatch sample scripts. And you can use these CloudWatch monitoring scripts as templates that are the starting point for modifying, for making these application custom alarms. So you don't have to start from scratch. So a good practice is to take these sample scripts, play with them, and then use those as a baseline for your own custom metrics. So now we download these custom monitoring scripts. We unzip them, and you can see that the output is a couple of files on a Perl module. First we need to edit the AWS credentials file. Basically we need to enter our keys here. And then, because this is a Linux system, you will be editing anything from with the Chrome tab. You can have the operating system, the daemon here and there, execute regularly certain scripts. So in this case, we are going to be making a run tab script that every minute executes one of these AWS example scripts, and it will collect the memory utilization of this particular instance. Here we are. We have installed this new Chrome tab. Okay, I just reinserted my microphone. There was a problem. Sorry about the short delay. I hope you can all hear better now. Good. Okay, let's continue. So basically we made a custom metric there using the example scripts. We made a run tab. And now the Linux system is every minute collecting the memory utilization and feeding it into CloudWatch. Then in the CloudWatch console, we can see that there is a new metric available. It's called memory utilization, and then we will be able to see the graph. So this is an example of getting custom CloudWatch metrics. Now next, let's take a look at the third-party services. So you are leveraging not only AWS services for things like compute, maybe databases, you are likely also using third-party services to implement other functionality that you need. They are typically black boxes, which means that you can't get into the services, but you can still monitor things. You can, for example, monitor the request that you make to the service, the number of associated responses, how successful was the request response, were there failures when you tried to ask the service to do something, and what is the latency, what is the delay when you actually interact with this external service. So here we have an example of an actual measurement and visualization of studying what is the quality of service, in this case of DNS, domain name service. So in this particular example, this is again a real-life example. There was a DNS server, this is not Route 53, this was an external DNS server that was behaving a little bit badly. So with this Scatterplot here, we can see that most of the DNS responses fall between 0 and 5 seconds, so that is fine. We can see some interesting striping or banding here, that somehow the DNS server is responding with pretty regular intervals here, which is a bit weird. But the problem is visible there where we have highlighted it in green. Many of the DNS requests get a 29-second, you can see a kind of line there, or 30-second, exactly 30-second response back. So basically, there were timeouts, there were failures, and you can see the failure mode here implemented as a regular 30-second latency for the error response. And again, this is a quite low-level analysis, low-level measurement of the quality of service of an external service. But we are dependent on these external services, so we want to know how well they are behaving. So at least we can contact the service provider in this case. Or in some cases, we may want to disconnect from this badly behaving service, otherwise it's causing a cascading domino effect in our product. That's called degraded mode. So for example, if the external service you're relying on is behaving badly, you may want to make a decision to disconnect the service while it's behaving badly and continue without it. So moving your transaction to degraded mode. For example, Netflix states the example that if the recommendation engine is unavailable, they will switch to a static top 10 list of movies and they can move on with serving the customer request. So that was third-party services monitoring. Now let's focus on your application. How would we measure your application? It's the final axis in our picture here. We are talking about measuring top to bottom, the entire technology stack. So basically, don't just measure some of these things. You should be measuring all of these things. Well, if we go from bottom up, the easy-to-instance health and metrics you can get from CloudWatch. But after that, you're talking about the guest operating system within the instance. So you will want to be measuring and monitoring the guest operating system services, your JVM or language interpreter. Maybe you're running web servers, maybe you're running database servers that you're managing yourself within the EC2 instance, your application servers, and ultimately your application code itself. You need to measure the entire stack top to bottom. And here's an example of application internal metrics. This is again a real-life example. On the top here, we can see some workers. So this is a multi-threaded application that has by default roughly 300 workers. During the day, you can see that the number of free workers is decreasing. And at some points, the number of free workers goes to 0. That means that there's not enough multi-threaded worker threads available to serve all the incoming requests. And the second graph on the bottom shows the result of this. As the application runs out of the worker threads, it starts buffering customer requests. And the immediate impact is that this is a delay. This is adding latency to the customer requests. And if it buffers them too long, ultimately the client side will time out and display an error. So this is a nice example where you really want to have application internal metrics showing the state and health of your application internally, not just the external interfaces in and out of your application. You want to zoom into your application. So we've been talking about collecting. The next phase would be then to analyze the information that we collect. And here we have AWS Big Data Services. So the recommendation is that for many of these analytics needs, you can look at the AWS Big Data Service portfolio. We have handy services for storing your data, such as Amazon S3, object store with unlimited capacity, 11 nines of durability, the extremely fast DynamoDB with consistent performance that you can set. We have Elastic MapReduce, Hadoop as an easy to manage, fully managed service, Redshift, data warehouse, petabyte scale, data pipeline that can help you move your data around from storage systems to analytics. And then we have Kinesis, for example. With Amazon Kinesis, you can implement real-time measuring and monitoring of your applications. But big data analytics is a large topic of its own, so that's not fully in the scope of this webinar. You will want to take a look at, just a second. Just a second, we have a technical problem now streaming the data out. Just give me a moment, please. Okay, hopefully everything works now. Sorry about that. Not sure if you saw this. I'm briefly going to show you the application internal metrics. I was talking about the workers free on the top and the buffering on the bottom. Then analytics, the AWS Big Data Services portfolio, which is a topic of its own, so it's outside the scope of this. Apologies, we seem to have a problem now with GoToWebinar. I have not paused my screen, but it's not updating to the viewers. Apologies, viewers, please hang on a bit. We have a technical problem with the webinar system now. We're trying to fix that. Okay, finally. Apologies about this webinar system issue. Now we are back. So really sorry about the delay. In the interest of time, I will just continue. So you may have missed some of the slides if they were frozen on the screen, but let's continue anyway. We will be uploading the slides anyway to SlideShare, so you will be able to see them there. So, analytics, big data portfolio, moving on. Once you have collected your data, your information, you have analyzed it with various tools, you will need to display. You will need to display the actual metrics and state of your system. So here's an example from Etsy, one of the companies running their systems on AWS. This is their dashboard. This is their dashboard in the office where they are monitoring in real-time or near real-time, many of their key performance indicators or KPIs. So here's an example of one type of visualization. Everybody knows the graph. So a graph gives you or shows you values of a metric over time at a certain sampling rate. And here I have highlighted that you can see transactions per second for this particular product. Everything is happy, except in the middle here, within the green box there. You can see that the transactions per second that the server was doing went down to 0. And it was down at 0 for several minutes. So that is an outage of this particular application. So this is a graph. Something to note about graphs. It's very nice, it's visual, you can see it very easily, very commonly used. There's something about the sampling rate. So the sampling rate means how often should I measure my values? Well, that depends on what you are measuring. And that ultimately depends on the rate of changes in what you are measuring, which is the frequency of your changes. Now it gets a bit, let's say, theoretical or physical here. There's something called the Newquist frequency. So Harry Newquist, he came up with this theory that was proven. You should be measuring at least twice as often as your values are changing. So if we look at the bottom left here, we can see that there's a signal. Basically, what is the signal? Those are the values that are changing in your metric, like transactions per second, maybe your internal application buffers, number of threads available in your application, etc. In this particular case on the left here, we are measuring those arrows at twice the speed of the rate of change. So based on the measurements on the bottom left, we have the resulting signal that we have captured or measured. And you can see that it's pretty much able to capture the rate of changes. So it captures all the changes, and it captures the amplitude, so the minimum and maximum values. So both the amplitude and the frequency of the original signal. What is a signal? Your rate of change of your system. However, if you start measuring slowly, slower than your rate of change, then some bad things start to happen. So let's switch our attention on the right-hand side. The original signal or rate of changes in your system is the red graph. The blue graph represents what you are measuring. So on the top there, on the top right, the rate of measuring something, or the sampling rate, is 5 times higher than your system change rate. So when you measure 5 times faster than your system is changing, everything is fine, you are able to capture and reproduce the signal as it is. Then we are sampling a little bit slower, but we are still happy on the second one. But as we move down on the graphs there, as our sampling rate starts getting slower, it's no longer able to capture the original system changes. And when you look at the bottom two there, you can basically see that when we have a lot of changes, a high frequency of changes in the original system in red there, but we are not measuring very often, then our measured graph looks very strange. Basically, then we have a random graph. It's not telling us too much. So when you work with graphs, you have to take the Newquist frequency and sampling rate into consideration. And then, interestingly, as we are measuring changes in values over time, that is basically a signal. So our system measurements are producing a signal. Because it's a signal, we can do digital signal processing. One of the ways is linear regression. Well, it sounds complicated, but it's just a trend line. So here we have another live example again, or real-life example. This is a metric showing the number of inodes utilized in a Unix system. An inode is a file descriptor. Basically, when the number of inodes utilized goes to 100, that storage volume in the Unix system is not able to create another file. It has exhausted all the file handles. So with this linear regression of the actual metric over some time, we can see that the number of inodes are being consumed in the system. And this is actually a prediction and a projection, and this graph was able to prevent a crash of a system. Because the operations people, the support people were able to see with the linear regression that after a few weeks, for example, this volume will not be able to create new files and the application will crash. So this was preventive maintenance doing digital signal processing on the measurements. Moving even deeper into this theory or application, an example here is Netflix Crier. So what Netflix have done is that they measure and then they apply both linear regression and fast Fourier transformations to the signal. With fast Fourier transformation, they can detect repeating sine wave patterns. A lot of the traffic is actually repeating over certain time periods, so they can detect that, and they can also detect anomalies, strange peaks which are not normal. So Netflix Crier is a really interesting predictive reactive autoscaling engine using linear regression and fast Fourier transformation for the measured signals from their system. There are some beautiful blog posts on that at the Netflix Tech blog. Here's another visualization example. It's the Scatterplot. You saw one earlier already. So with the Scatterplot, you can basically see, in this case, that the delay, whatever of the system response, was mostly clustered under 0.1 seconds in this case. But there are some cases when the system is responding slower, and you can see an interesting pattern there at 0.35 seconds. There's clearly something unnatural there, that there's a cluster of responses at 0.35 seconds. So this can help your application developers detect why your system is behaving in a certain manner. Another nice way of visualizing things is to use the box plot. With the box plot, when you measure something, you can basically have a median, which is the normal value. You can have the maximum and minimum range of your different values. And then you have the normal curve and histogram. With these guys, it's easy to visualize the outliers and the ends of the distribution, that okay, most of your users get this kind of experience or this kind of latency, but you have these outliers. For example, at Amazon, what we do is that we focus on improving the worst case scenarios. Then you move the whole bell curve and everybody benefits. Ultimately, collecting, analyzing, and displaying metrics is useless unless you act on the results. So let's see how humans can act on the results. There's something called the OODA loop. It basically means that you observe something, you orient yourself or your system based on the measurements and observations. You decide what to do next based on the information, and then you act. And as you act, you start over again. You act, that's a change, then you observe, orient, decide, and act again. In this manner, humans can use the information to make rapid decisions and changes to the system. Now let's see how we could automate, at least partially, the human actions by combining AWS CloudWatch monitoring with Amazon SNS simple notifications, and then third-party services like PagerDuty. So you can have automated alerts going to the right people who are basically operating and servicing and supporting your systems. So here we have automation driving human actions, hopefully, once they get the PagerDuty notification. And then ultimately, you want to have fully automated actions. So one of the examples here is AWS Autoscaling, where the CloudWatch metrics are automatically used to determine the size of the pool of your servers for any given service tier. So simply, you can set the rules, minimum, maximum, number of instances, and then the thresholds after which the autoscaling will react. So autoscaling can add more instances when you need more instances to serve the traffic, and it can remove instances to save money. But this is an example of measurements and automated actions on your system based on the measurements. All of this is actually not so new. It's quite normal, if you will. Cloud computing is new, but monitoring something, trying to reach a target state, and then ensuring that you are at the target state and then doing changes to actually reach this target state, that is normal. That happens in your fridge. That happens in your oven even. So what's common between an oven and a cloud computing application? it could be that they both might be using a PID controller. So Pid Controller is something that systems have used a long time to have inputs into the system and a target condition like temperature of the oven or performance of a cloud application. And then analyzing what should be done to reach this target condition or maximum transactions per second at a certain latency, then changing the system, measuring the changes, measuring the impact, and feeding it back as a feedback loop into the system again. So on the right-hand side there, you can see an example of the system reaching a target state automatically with this kind of Pid controller algorithms and feedback loops. The same can be used in many cases to control applications, services, and systems, even though they are in the cloud. Now to finalize, it's not just AWS services. There's a large ecosystem of both open source, free and commercial tools and services that can help you do monitoring, the analytics, the visualization, and then finally acting on the measurements. So here I have just collected a few, just a sample of these really handy tools and services, and there's a lot more. And if you're interested in learning more, you can of course visit the documentation at awsamazon.com for our services. And one nice source of information is Monitorama. So Monitorama is a conference that focuses on monitoring, and there are really brilliant presentations in Vimeo if you search for Monitorama. Thank you. Sorry about the delay earlier. We had a problem with the GoToWebinar system, but luckily it looks like it was sorted out. We had a few minutes outage there that we were able to measure. We had bad quality of service in your client side, but then we recovered with the actions that we did to the system. So it was not intentional, but that's what happened. Thank you very much. We will upload the slides to SlideShare so you can see all of the ones that you may have missed when the system was not updating the screen. And ultimately, please give us your feedback. So we have a survey here. Please complete the survey. Let us know what's good, what's not, what you want to see going forward at these events, and how we can deliver them to you better. And now, we are soon running out of time. We can still have a few minutes of questions and answers in the online system, but we will be muting the audio now. I would just like to thank everybody very much for joining. Apologies again for the hiccup with the system, but hope it wasn't too disturbing, and hope to see you next time. Thank you very much.